Okay, so this week we're going to keep talking about this concept of method of sections. And I kind of really love this lecture because it's really where all the ideas we've talked about so far this term come together. And at the end of this, we will be able to figure out what all of the internal loads are on our elements. And remember, the whole point of everything we're doing is making sure that the reduced capacity is greater than the factored load. At the end of this lecture, we will be able to determine the factored loads on things. So those internal factored loads, we'll be able to figure out what they are so that next year we'll be able to sit and figure out what the reduced capacities of those members are so that we can say, yes, this reduced capacity is greater than this factored load. Now, there are two ways to do what we're talking about today. So we're going to be going through method of sections for beam analysis. I am going to show you, actually, I guess there's technically three ways. There are two mathematical ways. One is using integrals and derivations. Obviously, calm down, nobody panic. We're not going to be doing that. I'm going to be showing you basically a rationalized way of doing that. Technically, we're still doing that, but we're doing it basically from scratch. For those of you that remember how to solve for areas under a curve using integrals and derivations, you could do that. And I have had students in the past say they're a math major and they would prefer to do it that way. And I've said, no problem, have at her. But back then, all the problem solutions were by hand. So if they made a mistake, I couldn't give them the points because it was hard to track their thought process the same way. You guys are inputting things into Quercus, so do it as you please. That said, the way I'm going to show you is basically an easy version of that. It's the engineering version of that. And then at the end of the lecture, I'm going to do what I tend to do and show you some tables and charts that are not an easier way of doing what I'm going to teach you, but so many people have done exactly what I'm going to teach you that they've made some handy charts of it. But those charts came from exactly what I'm going to teach you how to do. So I also just wanted to kind of give a general recap. I'm feeling better. I hope most of you are feeling better. I know a large swath of people at Daniels all got sick. We all got sick around the same time. That seems like everyone who hadn't got it in the past 2 weeks. So I hope everyone's doing okay. Feel free to reach out to me if you're struggling. For exam, I know the exam time slot's been posted. I believe you guys are April 22nd from 2 to 5. I find out the same way you do by looking at the exam timetables. If you are somebody that struggles or needs accessibility services, please contact them. The exam is the thing I cannot deviate from without instructions from them. The administration checks up on me for this. So this is the thing where I really have to follow the rules. So if you need extensions or things like that, please reach out to them so that I can help you accommodate for those. Trying to think if there's anything else kind of interesting in the world. My kids are back in school. Dave, anything interesting going on?
Not a thing.
Not a thing.
Boring life.
I'm a lucky lady. I'm a lucky lady. Okay, so today's lecture, method of sections beams. The first thing we're going to do is we're going to go back and we're going to look at those types of forces again. I am still coughing a bit, so I apologize. Okay. It is also the first day I've been feeling good, so I'm feeling very energized. It's the first day I've had energy. Okay. So the internal forces, they're the forces that act internally on an object that cause no movement of the object in space. Distortion is something different. Distortion is deflection. that is not the object moving in space. So make sure you think about those as two separate things in your mind. They are typically pairs of forces or pairs of moments, which include an implied force and a reaction to hold it in equilibrium. Remember, this is what we did last week with our trusses. We looked at the object as a whole, and then if we said, if this object isn't moving, if we put a piece of paper over this and only talk about this, we know it's not moving because the other half of the object is what's holding it in place. So if we thought about the other half of the object as the reaction, we should be able to figure out what those internal forces are on that. So we were able to do that pretty easily with axial loads. Axial loads are always a great place to start. And next term, when we get into solving for the capacities of members, that we're going to do the exact same thing. We'll start with axial forces and then move on. But axial loads, people tend to really kind of get their head around. So what we're talking about here is if we have, if I am sitting on my table, obviously we know the legs are supporting this. And so the reactions are right there. I think everybody gets their head around it. But something is happening in this table. Me, as an applied load on this table, doesn't just magically transfer over to there. Something is happening in this table. There's internal things happening in this block of wood to transfer the loads to either end of the table. And we have to be able to figure out what those internal loads are. Everything's kind of gotten loose on all of the clamps for my camera, so it tends to wobble a little bit now. Okay, so axial loads we talked about last week. And we know there's shear and bending, and then we've talked about torsion before, but that's a little bit beyond the course. So axial forces were easy. That was compression and tension. Shear is this tendency for the two planes to slip past each other. As we widen that concept of the plane, it starts to look like it's skewing it. But we're acknowledging that there's really a plane right here, and 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 a plane right here. And that kind of amalgamation of all these planes is when people really start to try to talk about integrals and derivation. But again, we're not going to talk about it that way. But imagine that you've got an infinite amount of planes slipping past each other, and we're talking about it as a bit of a gap between those now. Okay, and then bending. We've drawn this diagram before. It is trying to do something like this. We can see that the top is squashing and the bottom is stretching. Or if we wanted, we could flip it the other way around, and the top is stretching and the bottom is squashing. We know squashing is compression and stretching is tension. We saw in our trusses last week that if we had a typical kind of form of a bending, it would squash here and stretch here. There was an example one where we had a moment connection here, or the truss was connected at one end and a load pointing downward on it, and we ended up with the top chord in tension and the bottom chord in compression. That one really seemed to throw people off. I didn't ask you to solve for the force in the top chord. I just asked you if the top chord was in tension or compression. And really, you could do a simple exercise of taking an eraser and holding it here and pushing downward and helping you understand if the top is in tension or compression. It's not a bad thing to do all of the time. You remember those little exercises that I've suggested you do, like make a prediction of what you think is going to happen? Trust your instincts here. Sometimes it's easier to forget about all the math I'm teaching you and just pick something up and manipulate it and try to predict what the math is going to tell you. And I know you're thinking, if we did all that, why are we bothering with the math? Well, sometimes it's not as easy to predict. I'm usually trying to give you ones that are predictable so that we can solve and see the correlation there. But for some of the things that I'm working on that are very complex, that are working in 3 dimensions with trusses, with shared stiffness and multiple directions, the answers aren't quite as obvious. So knowing how to do the math is very important. So we've talked about our beams in bending, and we know that's really like a moment bending this way and a moment bending it this way. Well, we also know that we can represent a moment as a force couple. So this moment here could be represented as 2 arrows, and this moment here could be represented as 2 arrows. And we have a distance between them. So a force with a distance or an eccentricity is a moment. If we've got a pair of them in equal and opposite directions, this is a force couple or a moment couple right here. This is the equivalent to a moment. It'll cause it to bend, but not translate. Okay, last week we talked about method of sections with trusses. So we had this truss, and I think you can intuitively understand that this top chord is going to be in compression. Remember, for internal forces, if it's pointing toward the node or cut that we're talking about, it's compression. If it's drawn away, it's tension. Okay, so we could have solved for this and determined that the top part of this truss is in compression and the bottom part is in tension. And we've got some tension in this web here. Okay, well, we know that we often break this up into its X and Y component, right? So no problem, let's break that up into its X and Y component. And we've drawn this cut in these right here, but it's the same thing along its whole length. Technically, this cut could be right here, like 0.000001 millimeters, right to the other side of this node right here. So these could really be drawn right here if we wanted to. So this could come down and add into that, because really it's the same as the force right here and the force right here. So we've broken this up into its X and Y components, and we've just added up the X's that are both going in this direction right here. Okay, so we've got a force going kind of along that plane. That looks a lot like our shear force. And look at this, a top element in compression and a bottom element in tension. These look equal and opposite, some distance apart from each other. We tend to talk about that as moment. Okay, so maybe we could redraw that as moment. Everything, all right.
Steve's not coming.
Good. So what if we just imagined all of that truss was just a blob? We know that we can solve for all of these internal members that make up the web of this truss. But let's just really, when we did this cut right here, it was kind of like what was happening internally over here was irrelevant. If we made the cut here, different story. But when we make the cut right here, this we could have just drawn as one big blob. Okay, so it's the same thing right here. I've just redrawn this and grayed out what's happening over here because I don't care about what's happening in the other spots. At this moment, a different cut, I would care, but not for this cut. Okay, so I've got the Y component of my web element, and I've got my top chord force, and then I've got the X component of my web element and my bottom chord. Well, what if I redrew these as an internal moment? Okay, so it seems like now, instead of drawing some unknown placeholders for the internal axial forces, if this was a normal beam and not a truss, I could draw some placeholders. I know that this object, there was more to this somewhere off in space to help determine what this reaction is. And then I've drawn an internal cut here, but this object isn't moving off in space. It's staying still because the object as a whole isn't flying off into space. So there must be something happening where this part of the object connects with this part of the object to have it not fly off in space. There must be internal forces there holding it in place. So instead of drawing that as a bunch of unknown axial forces, we could draw that as the unknown shear force and the unknown bending moment force holding this object in place. So that's exactly what we're going to do. It's the exact same system we employed for solving for trusses. It's funny, in some ways people find this part easier, even though sometimes it looks more complex. Okay, let's start with a simple beam. We have our unknown reactions here. It's a pin roller support, and we have a 20 kilonewton point load at the midspan of this 15-meter beam. We want to know what the internal forces are on this beam, because we know next term we're going to figure out what the capacity of materials are, and we'll need to know if the reduced capacity is greater than the factored loads. But we need to know what the factored loads are this term to be able to do that. So we need to know what internal factored shears are on this and what internal factored moments are on this. And we need to then take the worst ones anywhere on this member so that next term we can find the reduced capacities and make sure this beam works. Okay. That's all of the concept learning we're going to do. Almost everything else we're going to talk about today is math equations. So I'm going to turn this down and we're going to jump in to the math part now. It's a bit of a gray day, so I want to make sure we don't get too many weird shadows here for you guys. I probably should have invested in those fancy lights, but that might be pretty good. I think that's all right. Okay. So the very first thing we had, so this is beam 1. All right, this is the very first beam we're going to solve with method of sections here. All right, we have a 15-meter long beam. And they told us there was a point load applied at the middle of that. In fact, they even told us what that applied load was. It was 20 kilonewtons. I'm just going to go shut the door to the kids' room. Dave's taking a call. Okay, here we go. All right, we've got a 20 kilonewton point load applied. And we know that there are some unknown reactions holding this thing in place. It's probably going to be detailed like a normal, typical beam, meaning that we would have a pinned roller connection. Okay, so we've got a 20 kilonewton point load applied at the midspan of a 15-meter long beam with a pinned roller connection. Okay. Step 1, we need to figure out what the reactions are for this, all right? So I guess step 1 was draw the free body diagram. Step 2 is solve for the reactions. We can't solve for the internal forces if we don't know what the what the external reactions are. All right, luckily we have 3 handy equations to make sure that this isn't moving up and down, sliding back and forth, or spinning in space. Sum the forces in the x direction, with everything going that way being positive. Our x equals 0. Okay, let's sum the moments about the z-axis where everything going in that direction is positive, and let's pick R1 right here. That's where I'm going to put my thumbtack. I'm lazy. I pretty much always put it there. You could put it over here if you wanted. It doesn't matter, but I'm lazy and I'm always going to solve for it right here. And we want to know what it takes for what R2 needs to be to make sure this thing doesn't spin in space. Okay, thumbtack right here. My 20 kilonewtons spins it in that direction. Curl my fingers in the direction it's going to spin. My thumb points into the page. That tells me it's negative. So minus 20 times the eccentricity from the thumbtack, or 7.5 meters. Thumbtack right here. R2 tries to spin the page in this direction. My thumb then tells me that it's coming out of the page, which means it's positive. So plus R2 times 15 meters. All right, I can rearrange this and I can solve for R2. Bring the 20 times 7.5 over here, and it's positive. Oops. 20 times 7.5 equals 150 divided by 15. I get 10 kilonewtons. We could tell that pretty easily. 20 kilonewtons in the middle, half goes over here, half goes over here. You intuitively know that this should be 10 kilonewtons. But I like to go through the process so that you can see it mathematically, so that you start to have the rhythm worked out for the ones that start to get a little bit harder. Let's sum the forces in the y direction, with everything upwards being positive. Okay, well, we've got R1 going upwards, we've got 20 kilonewtons going downwards, and we've got 10 kilonewtons going upwards for our R2. That was our R2, and we filled it in with our 10 kilonewtons. We can rearrange this, all right, and the 20 kilonewtons comes over here and is positive. The 10 kilonewtons comes over and is negative. So 20 minus 10, 10 kilonewtons. So this matches pretty much what we expected would happen here, right? Well, now we want to solve using method of sections. All right, method of sections. But we've never done this before, and we're a little bit nervous. Where do we cut this? Okay, so the very first cut I'm going to do, I'm going to pick an easy one. I'm going to cut it right, I'm going to cut it right here. Okay, I'm going to cut it at halfway along this point right here. We're going to start to simplify this a little bit. In fact, eventually what I'm going to do is I'm going to do this with no numbers, and we're going to go through and solve this without numbers. That's going to be what we're going to do next. But first, let's do method of sections at 3.75 meters. So we're going to say at this point right here, let's do a cut. So I've got a cut right there. We know that for this particular application, we have 10 kilonewtons right here, 0 kilonewtons right here. We know that we're cutting this at 3.75 meters, and that for this, we know that this whole object isn't moving or sliding or spinning, so this section can't be moving or sliding or spinning. But there's a load applied here. So if there's a load applied here, what's stopping it from moving or sliding or spinning? The rest of the object is what's doing that. So there must be some internal force here that's stopping that. And we know that the internal forces could be a shear and a moment. But we don't know what they are. So let's draw an internal shear and an internal moment, okay? Here are the questions I always get. Question 1, why did I draw my arrow with only half a head? That's kind of a shorthand thing that engineers tend to do for shear. Remember how shear is those two planes sliding past each other? Well, we're saying that we're splitting, it's such a thin plane, it's almost like we're slicing the arrow in half. So we're like really cutting right through it here. So this is telling me that this side is slipping relative to this side. So this is more or less just shorthand engineering. I could have drawn a regular arrow here, but I'm an engineer. I've been doing this since I did my very first statics course for 23 years, I think. So I am in the habit of drawing my shear arrow with only half of the arrowhead. You don't have to draw it that way, but that's why I draw it that way. The second one is, why did I draw it downwards? Almost everything else I've ever done, I've always drawn positive. Remember, I always drew everything in tension. I always draw my reactions going up. Look, even here, I've drawn my unknown moment going in the positive direction. Why am I messing with you poor suckers and drawing my shear down? My answer to you for that is that most engineers will do this simply because we know that this is going to result in a positive answer for us right here. And we start with a positive answer on this side and work across. You are going to benefit from my years and other people's 100 years of knowledge on how to solve this. You could start with this drawn the other way and you get a negative answer, and that would be okay as long as you're consistent. Don't switch around what way you draw this, because consistency is key here. And this is like a good rule of thumb all the time. Be consistent about your methodology. I am always going to draw my unknown shear as a negative arrow and my unknown moment as a positive moment. And you're going to see that in a little bit. Remember in axial loads, negative told us that we drew our arrow wrong and it meant it was in compression, and a positive meant we drew it right, which meant it was tension. So tension and compression have really different kind of effects on what happens within our structures, especially for material design later on. Shear, we actually don't care that much if it's positive or negative. It doesn't have an implication on how the material behaves. Shear is shear. But keeping track of positive versus negative is important because it tells us where we cross datums. So the only reason we care about a positive or a negative value in shear is to complete our methodology. But once we get all of our answers and everything solved, a positive versus a negative is absolutely meaningless to us. And you'll see what I mean when we get to that. Okay, so I have an unknown moment and an unknown shear holding this section of beam in place, because we know that this unknown shear and unknown moment right here that are happening right here have got to be resolved in the rest of the member there. Okay, well, luckily we have 3 handy-dandy equations that we can use to solve this. Let's start with summing our forces in the y direction and seeing what it takes for it to be in static equilibrium and everything upwards being positive. Okay, well, I have 10 kilonewtons going upwards, and I have my shear force going downwards, so minus V. Okay, I can rearrange this. V equals 10 kilonewtons. See, it was really handy. I ended up with a positive number now because I drew my shear downwards. I'm not looking to have this always be a positive, but most of the time in simple, boring old beams, a positive shear on this side is what we kind of like to go for. So always draw your unknown shear as a negative. And really interesting things, you can start to tell interesting things then. Okay, let's sum our moments about the z-axis. So everything is 0. We want this to be in static equilibrium, and everything going in that direction is positive. Where am I going to spin about? Well, remember before when we were looking for reactions, I always liked to do it right here. When I'm solving for a method of sections of a beam, I like to actually solve right here because my shear goes right through it. And it means I don't even have to worry about it. I don't even have to solve for the shear first, because to be a moment, you have to have a force and an eccentricity. If I put my thumbtack right here, my unknown shear passes right through it, which gets rid of one whole complication right off the bat. So this is all about really simplifying a process. So I'm going to put my thumbtack at 7.35 or at 3.75 meters. So thumbtack right here. To be a moment, you need a force and an eccentricity, or be a moment. Well, the shear passes right through it. The zero passes right through it. I have 10 kilonewtons right here. It's trying to spin my paper in that direction. Curl my fingers, point my thumb, and that's spinning in the negative direction. So I have minus 10 kilonewtons, and it is 3.75 meters away from my imaginary thumbtack. And then my moment, my unknown moment, is just spinning in the positive direction about that. Remember, I guessed that it was positive. I'm just drawing it positive. So plus m equals 0. I can rearrange this. So I'll multiply 3.75 by 10 and bring it over to the other side. M equals 10 times 3.7. That was my chair, by the way. 37.5 kilonewton meters. Okay, so 37.5 kilonewton meters. So for this member to be in static equilibrium and support this 20 kilonewton point load with reactions of 10 kilonewtons over here, it means at this point right here on this beam, there is an internal shear force of 10 kilonewtons and an internal moment of 37.5 kilonewton meters. We have some information. We now know we need a member that can resist 10 kilonewtons of shear and 37.5 kilonewtons of moment. Great. But, how do we know if that's the worst moment and the worst shear? Looks like we might have to cut this in more spots to figure out what the worst moment and the worst shear is. We don't want to just support 37.5 kilonewton meters. We want to make sure this beam is strong enough to support the worst moment it sees along its length. So how would we go about that? Okay, I'm going to tell you now where I cut my beams. I cut my beams whenever there's a major transition, okay? If there's a line load on it, anywhere along the line load is fine. You can cut it at multiple spots, it's up to you. If there's no load on it, I cut it at every major transition. So where do I have a major transition? Well, I have where reaction 1 is. So imagine that I cut the beam right here. And you're thinking, that's right at the support. Well, I'm going to tell you I'm cutting it at 0.00000000000001 millimeters past that point right there. Okay? Then I cut it right here. I'm going to cut it right here. I'm going to cut it right at 7.5 meters. But what I really mean is I'm going to cut it at 7.499999999999999 meters. And then I'm going to cut it again right here at 7.5000000000000000001 meters. I'm going to cut it right here, and then I'm going to cut it right here, or 0.0, or at 7. Or at 15, at 14.999999999999999 meters. Okay? We don't know what's going to play out there, but those, like, we could cut it again right here, and we could cut it here, and we could cut it here, and we could cut it right here. But I think we might get a good idea of what's happening along this beam if we cut it in those spots. So essentially we're going to say we're going to cut it at 0. We're going to cut it at 3.75. We're going to cut it at 7.5 and 7.5, but we know really we're saying just a hair of a fraction on this side of the 20 kilonewtons, and then just a hair of a fraction on that side of the 20 kilonewtons. And then we'll cut it again at 11.25, and we'll cut it at 15 meters, but really we're saying just the tiniest amount before the support reaction. Okay, so we've already cut it at 3.75 meters. Don't worry, things are going to get a little bit easier. We're not going to be cutting it all the time at 6 points. Because you could imagine you could have beams, if we had had one with like 5 supports on this, we would have to cut that a lot of times. So after we go through this process, we're going to find a way that we can do it that makes it a little bit easier. Okay, so let's do method of sections at 0. At 0 meters. Or if you want, if you have a hard time understanding what I'm talking about, we're saying we're really cutting it at we're cutting it just on the other side of that support. So small that any number we multiply it by, we would effectively say is 0. All right? Like we were talking about a moment, which is a force times a distance, that would pretty much result in a 0. Okay, let's implement that. Let's take a look at that. So I'm going to draw this like this. I am going to say that's 0 meters. We know that I really mean it's this number, essentially. We know that we have a reaction here of 10 kilonewtons and 0 kilonewtons here, and an unknown shear and an unknown moment holding this end of our beam in place. Sorry guys, I'm just going to take a drink of water. Okay. Okay, so let's now go to our handy dandy equations. Did you notice that I didn't have anything to solve for in X here? I only had 2 unknowns. We have 3 equations, but I didn't really need it for this problem. I solved my 2 unknowns in the very first 2 equations. Next week, we're going to do a problem that also has axial thrown into it. So we're going to look at one that has both an unknown axial load, an unknown shear, and an unknown moment. Okay, let's sum our forces in the y direction with everything upwards being positive and see what it takes for this to be in static equilibrium, or for the sum of all of those forces to be 0. All right, we have our 10 kilonewtons upwards, and we have our unknown shear downwards. Rearrange, shear equals 10 kilonewtons. Okay, that was the same. So right here there's 10 kilonewtons of shear, and right here there's 10 kilonewtons of shear. That seems interesting. Let's sum the moments about the z-axis with everything spinning in that direction being positive, and we want to know what it takes for this to be in static equilibrium, and I am going to sum my moments about this point right here, which is point 0, because that distance is 0. All right, so my thumbtack is right here. My 10 kilonewtons is causing it to spin, but that distance is 0. To be a moment, you need a force and an eccentricity, but my eccentricity is 0, so there's no moment. Yeah, I know, it's 0, 0, 0, 0, a gazillion zeros, and at point 1, or 0, point gazillion zeros 1. If I multiplied that, my moment would be just 1 0 less, or point, like, we're talking about such a small number. So really, that doesn't cause it to spin. My shear passes through it. It doesn't cause it to spin. My only thing causing it to spin is this unknown moment. Point my thumb. It's causing it to spin in the positive direction. So plus m equals 0. Well, that was easy. Moment equals 0. So at this point right here on our beam, we have 10 kilonewtons of shear and no moment. This makes sense. Remember, this is a pinned roller condition. There is nowhere for the moment to go. We cannot accept moment right here. So it's a darn good thing there is no moment there. If there was moment there, we would have to have a reaction of some sort that could take moment. And remember, in steel, detailing a moment connection is really hard. We don't like to detail moment connections in steel unless we have to. I'm going to show you an example next week where we do, in fact, have moment at the end of a beam. But we try not to do it. Okay, so we've cut here and we've cut here. Let's cut just before our 20 kilonewtons. So let's do method of sections at 7.5 meters. And for those of you that really want to understand what I'm talking about, I'm saying just before the 20 kilonewtons is applied. So really, remember the 20 kilonewtons is applied right at 7.5 meters. So I'm saying at 7.49999 meters. Really, effectively, so many nines that if I was entering it into my calculator, I'd put in 7.5. Okay, let's draw this one. We can tell ourselves that this is 7.5 meters. I've got my reaction of 10 kilonewtons, 0 there, and an unknown shear of V and an unknown moment. These have to be there to hold this thing in place. We don't know what these are, but we know the other half of the beam is there. So this is what must be happening in the other half of the beam to hold this side in place. Let's sum our forces in the y direction with everything upwards being positive. Okay, we've got 10 kilonewtons upwards minus V equals 0. V equals 10 kilonewtons. See, I said in some ways this math is a lot easier. Don't worry, I'm gonna make it harder. But I want you to see the rhythm that we're going through here. Okay, now let's sum our moments about the z-axis, and we want to know what it takes for this to be in equilibrium. And I'm going to put my thumbtack right here at 7.5 meters. So here's my thumbtack right here. Shear passes right through it, so it doesn't cause it to spin. 10 kilonewtons tries to spin it in that direction. So I take my right hand and curl it in the direction it's trying to spin. My thumb points down into the page, which means it's spinning in the negative direction. So minus 10 times 7.5 meters plus our unknown moment. We can solve for m. Bring this over here. Becomes positive. 10 times 7.5 is 75 kilonewton meters. Okay, so for this member to be in static equilibrium, right here at this point, there is 10 kilonewtons of shear and 75 kilonewton meters of moment. All right, looks like we're starting to get some information. Let's now cut this on the other side. So I'm going to try to keep that right there so we can see it if we need to. All right, let's do method of sections at 7.5 meters, but really I'm talking about 7.50000.0001 meters. All right, so just on the other side of this 20 kilonewton point load being applied to it. Okay, so we can draw this here. We're saying it's 7.5 meters away, or this cut we're making is 7.5 meters. We have a reaction here that we've already solved for. This is what it takes for this overall object to be in static equilibrium. And now we're cutting just on the other side of our 20 kilonewton point load being applied. And we have some unknown internal shear holding this in place and some unknown internal moment holding this section in place. Okay? So we can sum the forces in the y direction with everything upwards being positive, and we want to know what it takes for this to be in static equilibrium. All right, we have 10 kilonewtons going upwards. We have 20 kilonewtons going downwards. And we have our unknown shear going downwards. Let's rearrange this. So we'll bring V over to be on the positive side. So we have 10 minus 20. We end up with minus 10 kilonewtons. Okay, everywhere on this side of the beam, we had plus 10 kilonewtons. And now something's happened and we've gone to minus 10 kilonewtons. All right, just hold on to that knowledge for now. We'll come back and we'll talk about that. But we've done the calculation and we've seen what it does here. I think what might be handy is if in a little bit we draw what's happening. And so we're going to start talking about not just drawing axial force diagrams, we're going to introduce drawing shear force diagrams as well, because that might help us understand this. Okay, let's sum the moments about the z-axis, where everything going in that direction is positive, and we want to know what it takes to be in static equilibrium. And because I'm lazy, I'm going to once again put my thumbtack right here where I made my cut. Okay, so my 20 kilonewtons passes right through it. My shear passes right through it. I have 10 kilonewtons trying to spin it, and my unknown moment trying to spin it. So my 10 kilonewtons is trying to spin it in the negative direction. So minus 10 times 7.5 plus my unknown moment. Can rearrange this, and moment equals 75 kilonewton meters. Okay, so we had a change in our shear and nothing happened to our moment at that point right here. Let's cut it right here at 11.25 meters now. So method of sections at 11.25 meters. This one's easy. We'll just cut it right at 11.25 meters. There's nothing interesting happening there, but we want to see what's happening in this transition zone, okay? All right. So we know that this is at 11.25 meters. We know we have some reactions here holding this overall object in place. We know we have a 20 kilonewton point load applied right here, and this was at 7.5 meters from the support. And this thing can't be moving in space or sliding or spinning because it's held in place by the rest of the member. Remember, the whole member isn't sliding or spinning or moving. So this portion of it can't be sliding or spinning and moving. So something must be holding it in place. We want to figure out what those are. We don't know what they are yet, so we're just going to label them as an unknown shear and an unknown moment, holding this thing in place. Let's sum our forces in the y direction with everything upwards being positive. We have 10 kilonewtons up, 20 kilonewtons down, and our unknown shear down. We can rearrange this, and shear equals minus 10 kilonewtons. Okay, so again, still not much happening in that zone. Let's sum the moments about the z-axes. We want to know what it takes to be in static equilibrium, or for the sum of all of those moments to be 0. And everything spinning in that direction is positive. I'm going to be lazy and once again put my thumbtack right at my section cut. So I'm going to put my thumbtack right here, or at 11.25. All right, if my thumbtack is right here, 10 kilonewtons is causing it to spin in that direction. I can curl my fingers in the direction it's trying to spin, and I point my thumb down. Okay, so my fingers are curling, my thumb's pointed down. That means it's negative. So minus 10 times, and it's 11.25 meters away. Okay, thumbtack right here. I've got 20 kilonewtons trying to spin it in that direction. All right, curl my fingers in the direction the 20 kilonewtons is trying to spin it. Point my thumb, that tells me it's in the positive direction. So plus 20 times, and the 20 is this distance away from my cut. So what's this distance? Well, it's 11.25 minus 7.5. We can calculate that. 11.25 minus 7.5. All right, 3.75. All right, 3.75 meters away from that cut. Shear passes right through it. So we're left with an unknown moment trying to spin it in that direction. All right, we've purposely drawn it positive. So plus m equals 0. Let's rearrange this equation and solve for our unknown moment here. Okay, we can bring that over and it becomes positive, and we bring that over and it becomes negative. So we have 10 times 11.25 minus 20 times 3.75. And we end up with 37.5 kilonewton meters. All right, we've got a bit more information. I had suggested we make one more cut. We're going to make this one right before the reaction at this end. So just like the tiniest fraction of a hair away from the support. So let's do method of sections at 15 meters. But really what I'm saying is I'm doing this cut at 14.999 meters. If I plug this into my calculator, it's effectively 15, but we know it's just the tiniest hair before we actually get to that support reaction. Okay, so let's draw this beam. We've got our reaction here of 10 kilonewtons. We've got our applied load here of 20 kilonewtons. We know this is 7.5 meters. This is effectively 15 meters, even though it's just the tiniest hair away from that support, meaning that this distance is 7.5 meters. And something's holding this in place. So we have an unknown shear and an unknown moment holding this object in place. Okay? We can use our equations of static equilibrium to help us solve this. And again, this is just formalizing the fact that this can't be moving up and down, sliding back and forth, or spinning in space. So let's sum our forces in the y direction with everything upwards being positive. We have 10 kilonewtons up, 20 kilonewtons down, and our unknown shear downwards. So minus V equals 0. We rearrange this, and V equals minus 10 kilonewtons. Okay, let's sum the moments about the z-axis, where everything spinning in this direction is positive, and we're going to put our imaginary thumbtack right here where I made my section cut, or at our 15 meter mark. Okay, imaginary thumbtack right here. My 10 kilonewtons is spinning it in that direction. Point my thumb down. I have minus 10 times 15. Imaginary thumbtack right here. 20 kilonewtons is trying to spin it in that direction, or plus 20 times 7.5. The shear passes right through it, so it doesn't have an eccentricity, and I have my unknown moment in the positive direction. Just stop and think here for a second. If we end up with a moment in the beam right here, it has to go somewhere, and we have a roller support here. What do you think the answer to this is going to be? What do we need the answer to be in this beam right here? We need there to be no moment there. Let's see what we get when we solve this. All right. Bring this over and it becomes positive. Bring that over and it becomes negative. And we end up with 10 times 15 minus 20 times 7.5, and we get 0. Okay, so we've got some handy information. But let's see if we could do something with this. I always find it handy to draw these things out. Let's take a look what happens if we draw these out. Okay, I am going to draw my free body diagram. I'm going to draw another line here. I'm going to draw another line here. This is my free body diagram. This one's easy. They gave us this right in the question, right? We knew that this was 7.5 meters, and this is 7.5 meters. We've already solved for this. They gave us that this was 20 kilonewtons point load applied to this, and we solved for this and found that there was 10 kilonewtons here, 10 kilonewtons here, and 0 kilonewtons here. Let's draw out our shear force diagram in kilonewtons. Okay? What happened at 0 meters? What was the shear force at 0 meters? All right, at 0 meters, we had a shear force of 10 kilonewtons. So let's say that's 10. At 3.75, we had a shear force of 10 kilonewtons. At 7.5 meters, we did two things. First, we solved for it, and we found that it was 10 kilonewtons. And then right where they applied the 20 kilonewtons, it then switched to minus 10 kilonewtons. Look at that. Look at that jump. It's exactly 20 kilonewtons. And then at 11.5, we found it was at minus 10 kilonewtons. And at 0, we found, or at 15 meters, we found it was minus 10 kilonewtons. Look, I'm not drawing the minus here because in shear force, we actually don't care about the absolute value. We keep track of plus and minus to see what happens here. It's important when we're doing the calculations, but as an absolute value, we actually don't care that much. I often will hatch it just to help me see what's going on. Let's assume that this 20 kilonewtons was a factored load. What's the maximum factored shear force on this beam? Remember, we don't care about shear if it's positive or negative. It's an absolute value. VF equals 10 kilonewtons. The maximum shear force that this beam sees is 10 kilonewtons. So we're going to need a member that can support 10 kilonewtons of shear force. Let's take a look at our moment here. At 0, when we calculated this, we found that the moment was 0. So that's great. At 3.75, we calculated it and it was 37.5. At the halfway mark, it was 75, and it didn't matter what side of the 20 kilonewtons applied load, it was 75 kilonewtons. And then at 11.25, it was 37.5 kilonewton meters. And then again, at the end of the beam, it went down to 0 meters. This is our bending moment diagram. And this is in kilonewton meters. Not kilonewtons per meter, kilonewton meter. You guys are going to have to do this for your project. You're going to have to go through this process. You're going to have to draw me these diagrams for a series of beams. Let's put in our information here. Believe it or not, I take off marks for the wrong units. Make sure you pay attention to units. It's an easy thing to give you marks on. All right, and this was 37.5, and this was 37.5. This was 0, and this was 0. What's the maximum factored moment? Assuming this was a factored load, what's the maximum factored moment on this beam? MF equals 75 kilonewton meters max. Okay, great. For this beam right here, we know that it sees a maximum shear force of 10 kilonewtons and a maximum factored moment of 75 kilonewton meters. So we know that next year, our job is to find a beam that can support these internal loads. And so that's going to be our goal next year. This is what we needed to learn this year. You guys have gotten there. You've figured it out. But what happens the next time we do one of these? What if this was 11 kilonewtons? What if this 20 kilonewtons was applied at the middle of a 30 meter beam? We have to go through this whole process again? That seems like a bit of a pain in the butt. So let's just come back to our problem, or our slides here. Here is that problem I just did, fully worked out. And see right here, what if we didn't know what the value of P was? What if we didn't know what the value of L is? What if we did this problem with placeholders instead? So let's do this exact same problem where instead of being 20 kilonewtons, we know it's some unknown force P. And rather than be an exact length of a beam, we know that we're applying this unknown load at the midpoint of our beam. We're going to assume that this is a factored P, in fact, but let's go through and solve this exact same problem, everything we just did right here, but go through and do it with unknown values here. I'm going to stop this and go get some more water because it turns out I still don't feel great. Okay, let's draw out our same free body diagram, but we're going to use placeholders for everything, okay? So we know that this is 1/2 L and this is 1/2 of L. The whole length is our unknown length, L. We have an unknown force, P, in kilonewtons. Rx, R1, and R2. Okay, these are our unknown reactions that is going to hold this object in place. Okay? We want to solve for our reactions. Let's use our typical method. So, solve for reactions. All right, let's sum our forces in the x direction with everything going in that direction being positive. Rx equals 0. Let's sum our moments about the z-axis. Everything going in that direction is positive. We want to know what it takes to be 0. And let's solve it by putting our thumbtack at R1. We're going to imagine this spinning about this point right here. Okay, we've got P trying to spin it in that direction. Let's curl my fingers in the direction it's trying to spin it. My thumb tells me it's trying to spin in the negative direction. All right, so we've got minus P. And remember, to be a moment, you need a force times a distance, and P is 1/2 L away from our spinning point. So times 1/2 L. Okay. We then have reaction 2, trying to spin it in that direction. Curl the fingers of our right hand in that direction. My thumb tells me it's positive. So plus R2 times the full length L. Those are the only things trying to spin this about that point. R1 passes through it, so it's not causing it to spin, and Rx passes through it, so it's not causing it to spin. R2 is what we're trying to solve for here. So we can bring this over to this side and then divide by L. So we can rewrite this as, we can bring this over here, so it's minus 1/2, or it would be positive because we're bringing it over to the other side. It would be 1/2 PL. All right, so we would have R2, well, let's write it out. Let's take the time to do this. So we would rearrange this and we would have R2L equals 1/2 PL. Well, that's a pain in the butt to have L on both sides. Let's divide both sides by L. We get R2 equals P divided by 2. Doesn't this match with what you intuitively know? You put this load in the middle, half of the load goes to R2 and half of the load goes to R1. So we've done this. We've talked about this with unknown loads before. We've just formalized it with unknown loads. We did it back here with known loads and a known length, but we can do it with placeholders if we want. Let's sum our forces in the y direction with everything upwards being positive, and we want to know what it takes for this not to slide up and down. Well, we've got R1 going upwards, we've got P going downwards, and we've got R2 going upwards. So plus R2, R2 is P divided by 2. Okay, minus P plus half a P is minus half of a P. Bring it over to the other side. R1 equals half of P. So this matches exactly what we expected. We expected half of P go to each end of our beam. So this matches exactly what we thought. Let's solve for the internal forces now. So where do we cut? Like, do we pick cutting at 1/4 of P or L? How do we do this? Well, I'm going to make a suggestion. What if, since we don't know what these numbers are anyway, let's use a placeholder X for cutting anywhere from just before or just after R1 to anywhere just before P. So let's cut at, well, this is method of sections at X equals 0 to 1/2 L. So we're going to call it X, and we know that it's representing anywhere from cutting right here all the way over to here. We're just going to use a placeholder X. It doesn't matter if it's 0.00000000001, 1/4 L, or just a hair shy of 1/2 L. Let's try it. Let's see what this looks like, okay? So we're going to put our length right here. We know that we've solved for this, and this is 1/2 P. All right, so we've already solved for that reaction. Just to be thorough, I'm going to draw that in there. This is some unknown length X. We just know that this X is somewhere between 0 and half of its length. And something that is holding this in place. Some unknown shear and some unknown moment is holding this in place. But we don't know what the values of those are. So let's go through our normal process. Let's sum the forces in the y direction with everything upwards being positive, and we want to know what it takes for this to be in static equilibrium. Okay, we've got 1/2 p going upwards, and we've got v going downwards. Let's rearrange this. Hold on a second, I'm going to sneeze. Just a oh, sorry guys. Okay. So we've got 1/2 p minus v. We rearrange this, and v equals 1/2 p. So anywhere along this length right here, this half of the beam, v equals 1/2 of p. Well, that seems to match exactly what we calculated when we had numbers. On this half of the beam, anywhere from here to here, our shear was 1/2 of our applied load. Okay, this is cool. This seems like a much quicker way to be doing things. Let's sum the moments about the z-axis, and we want to know what it takes to be 0. And we're putting our thumbtack right here at x. Remember, my habit for this is to do it at where the cut is. So x does not, well, it kind of does mean the x-axis. I'm cutting it at the length x along the x-axis, but we're spinning about the z-axis. Okay, so we're going to put our imaginary thumbtack right here. So v is passing right through that cut. Put our thumbtack here. 1/2 p is causing it to spin like that. All right, that's spinning it in this direction. Use my thumb. That tells me it's in the negative direction. So minus 1/2 p. But remember, to be a moment, you have to have a force and an eccentricity. P is happening x away from my cut. So times x. V passes through it. It doesn't cause it to spin. And my unknown moment is causing it to spin in the positive direction. So plus m equals 0. Let's rearrange this. Well, we just bring this over here. M equals 1/2 px. So depending where it is on the length of the member, we can, and this should be kilonewtons, and this is kilonewton meters, okay? Always remember the units. Sorry. All right, so that's kind of easy. It solves it for us anywhere along here. Let's now take a look at this side. Let's see what happens here. Method of sections at x equals 1/2 L to L. So let's do the same thing on this half of our beam. So now we're going to make our section cut after our load has been applied. And our placeholder x is still going to be the same, but now we're talking about x anywhere along this zone right here. So let's draw that free body diagram like this. We know we've got our applied load of P. We've got our reaction of 1/2 P and 0. This is happening at 1/2 L, and this is cut is happening at X, and holding this whole thing in place is an unknown shear and an unknown moment. And we want to know what it takes for this object not to move up and down, slide back and forth, or spin in space. And we know there's the rest of the beam holding this in place. So there's some internal reaction there holding this in place. And that internal reaction is our internal loads. So let's take a look and see what happens when we start to solve this here. So let's sum our forces in the y direction with everything upwards being positive. Okay, we've got 1/2 p going upwards, we've got p going down, and we've got v going down. We can rearrange this. We bring v over to the other side. 1/2 of p minus p, or a half minus a whole, gives us minus a half. So v equals minus 1/2 p kilonewtons. Let's go back and look at that one we did when we actually had numbers to it. Look, we were at half of p, and then we hit where the load was applied, and we switched to minus half of p. So that seems to match what we've calculated before. Let's sum our moments about the z-axis. Everything spinning in this direction is positive. We want to know what it takes to be 0. And we're going to put our thumbtack at x. So we're putting our imaginary thumbtack right here. 1/2 p is causing it to spin in that direction. So 1/2 p times our distance x. So times x, that's no problem. V is passing right through it, so it's not causing it to spin. We've got p trying to spin it in that direction. Wait, let's go back. 1/2 p times x. So 1/2 p, thumbtack, spinning it in that direction. Curl my right hand. That was a negative. So minus 1/2 p times x. Thumbtack here. P spins it in that direction. Curl my fingers. Right hand, thumb points up. That tells me it's positive p times. Now, what's the distance? Where is this? What's the distance here? Because this is our thumbtack and this is where it's happening. Well, this whole distance is x and it's not that distance. So it is x minus 1/2 L away. We don't know what x is, but whatever x is, it's minus 1/2 L from that. And then we have m, which we've drawn in the positive direction. So plus m equals 0. We can kind of clean this up a tiny little bit. So we have minus 1/2 px plus px minus 1/2 pl. So if you have a number outside the brackets, you multiply it by each part within the brackets. Plus m equals 0. Okay. Minus 1/2 px plus px becomes plus 1/2 px. Bring it over to the other side. So m equals minus 1/2 px. Bring this over to the other side, plus 1/2 pl. All right, so the moment is minus 1/2 px plus 1/2 pl, anywhere along this distance. I know, that's really ugly and a real pain in the butt, but don't worry, it's actually not that complicated. Once we've solved for this, we have it now. We never have to solve for it again. If we have a point load at the middle of the beam, it doesn't matter how long the beam is or what the value of that point load is. We've now solved for the internal moments. We just have to plug it into this equation now. We've done the hard work. So let's take a look. Let's actually plug some values into this. Let's see what this looks like. Okay, so let's do a little summary. So we know, so imagine this is our location. This is our shear in kilonewtons, and this is our moment in kilonewton meters. Okay? So, we know that at x equals 0 to 1/2 L, we solved for shear, and it was 1/2 P, and M was 1/2 PX, right? And then for x equals 1/2 L to L, we solved and found that it was minus 1/2 P, and then x was minus 1/2 PX plus 1/2 PL. Okay, I know you guys are all cursing this one line right here, but let's go through and solve for some of them. Let's solve it at x equals 0. All right, so at 0, we would use these lines of equations here, and our shear is 1/2 P. It is independent of x. All right, and our moment, we plug our moment in here, and we get 0. What happens at 1/4 L? So we're going to plug 1/4 L into this. It doesn't have L in it, so 1/2 P. Let's plug 1/4 L into this. So 1/2 P times 1/4 L gives us 1/8 PL. 1 divided by 8 PL. What happens at 1/2 L? So this shows up twice. So let's do it for this line, and then let's do it for this line. So just before our load is applied, 1/2 L is 1/2 P for shear. And the moment, 1/2 L, fill in for x. So 1/2 P times 1/2 L is 1/4 PL. At 1/2 L, on the other side of our point load being applied, we have minus 1/2 P. Let's plug in 1/2 L into this. Okay, so minus 1/2 P times 1/2 L is going to give us minus 1/2 times 1/4 is going to give us 1/8. So minus 1/8 PL plus 1/2 PL times 1/2 PL. This is going to work out to be 1/4 PL. So you can go through and plug that all in, but you're going to come out with the same answer. You're going to get 1/2 PL. All right, let's do 3/4 L. All right, there is no x in this, so if x is 3/4 L, doesn't matter here, we still get minus 1/2 P. We plug, sorry, yeah. So if we plug 3/4 L into this, we have minus 1/2 P times 3/4 L. So we end up with 1/2 2/4 minus 2/4 plus 1 or times 1. I'd have to go through and do it slow. I'm going to tell you, you can, if we plug that in as 3/4 L, you're going to work this out, and it's going to work out to be 1/8 PL. Trust me, go through and do it slowly. Go back to your basic, kind of do it step at a time. Just multiply everything out. It's going to work out to 1/8 PL. Let's plug L in. So let's do L. Again, this is independent. It does not have X in it. Let's plug L in here. Minus 1/2 PL plus 1/2 PL is 0. All right, this looks pretty handy for us. Let's just see. What if we had a 20 kilonewton point load on a 15 meter beam? At the mid-span, we had 75 kilonewton meters is what we calculated. So 0.25 times our 20 kilonewtons point load times our 15 meter beam. Look at that, 75 kilonewton meters. So we've done this. We've actually done this with actual numbers. This is a handy little shorthand. Let's redraw that free body diagram and our shear force diagram and our bending moment diagram. Okay, we have our unknown force P applied here. We know that we've solved for this, and this is 1/2 P, and this is 1/2 P. And we know that everywhere along here, this is 1/2 P positive, and then it switches down here to 1/2 negative. I'm going to remember to call this my shear force diagram in kilonewtons. And this is my bending moment diagram in kilonewton meters. All right. At x equals 0, the moment is 0. At x equals 1/4, so right here we had 1/8 PL. At half of L, didn't matter what side of the point load, we had 1/4 PL. At 3/4, it was 1/8 PL. And at the full length, the moment was 0. This is 1/2 PL, and this is 1/2 PL. Remember, once we're drawing it on the shear force diagram, we don't care so much about whether the value is positive or negative. We like seeing where it crosses over into positive and negative. And then our bending moment diagram, right up here, our highest value was 1/4 PL. So that is our moment diagram, and that's our shear diagram, but we always like to know what the maximum values are. So max VF is 1/2 PL, and max MF is 1/4 PL. Oh, sorry, these aren't L's. Just 1/2 P. Don't mind me. We can see it right here. These were all just P. There was no L in those. Scratch that out. So our maximum shear is half of the load, and our maximum moment is 1/4 of the load times the length. We did all of that work to prove that this diagram right here, this free body diagram, we have a maximum shear and a maximum moment that are pretty easy to calculate now. Do we ever have to go back and do another one of these? We have our information right here. We've done it. Now, I am going to tell you that, well, first off, in the exam, I don't see your work. You can do it whatever method you would like. I obviously can't check up on you for that. For your project, you are going to have to do method of sections for me. I have to be able to show the accreditation committee that I taught you method of sections and that you can, at least for a basic beam, complete the method of sections check. It is a requirement. We cannot get out of it. I'm not just being mean. It is stipulated that I teach you this. It's kind of just a given. But I'm going to show you that quite often it's pretty easy to check up on that. So let's take a look at some things here. All right, so that same problem has been worked out right here for you. And look, we even tested some things right here. So you can go through and test if P equals 20 and length equals 15, how these things work out here. Okay. This is where I want to kind of just talk about analogous point loads. What's an analogous point load? It's a handy little trick we use when we have kind of a temporary way we want to solve our problem. We can use it as a fake free body diagram temporarily. It is not, I repeat, do not ever draw the analogous point load on your actual free body diagram. I will 100% instantly take marks off if you don't have an actual free body diagram without the analogous point load drawn. So we know that if I sit in the middle of this table, half of my load goes over here and half of my load goes over here. Assume I was evenly distributed and I laid out flat on this table and I was perfectly everywhere on this table. You know that's the same thing as half of my load going to that end and half of my load going to that end. So how do you know that? Because you know it's the same thing. It does different things inside the table, but for determining what the reactions are, it's a pretty handy trick, and you know intuitively that it's the same thing. An analogous point load is basically just a formalization of that thought process. So, if I have a uniformly distributed load, and remember this tends to be how we draw a uniformly distributed load, we can, for the purpose of determining reactions, whether they're an internal placeholder reaction or the actual reactions of the overall section, we can use an analogous point load free body diagram to help us determine those reactions. It is not the total free body diagram, but it is a handy trick to help us to determine the loads for that static image of a problem. So, representing distributed loads as an equivalent point load can help simplify the diagram. It will have the same effect on the equilibrium of the free body diagram, so also the reactions, but not the total shear and bending moment diagrams of the individual sections that we do. So we can use an analogous point load temporarily to help us solve for reactions or of whatever section we're cutting. So I'll talk you through this. So if we had this uniformly distributed load on this beam, we know intuitively that it's the same thing as a point load that equals this at the middle of this load. All right? So this is our load, and every meter of it has W kilonewtons. So we would multiply W by D to find the total kilonewtons and plop it down in the middle of D. All right? So it's the same thing as a point load. That is the value of this uniformly distributed load times the length of that load at the middle of that load. This was the same thing we just did with me laying on the table. You intuitively understand this. We're just formalizing it. This is an analogous point load free body diagram that will now allow me to solve for these reactions. See, it's not in the middle of the overall length of the beam. It is in the middle of this applied load. What about this one? Well, we have a triangular load distribution over this length D2, but it doesn't start until D1. When we know the area of a triangle is the half of the whole, so W times D2 divided by 2 is going to be our point load, and it is going to take place 2/3 over of D2, but D2 doesn't even start until D1 finishes. So this is the equivalent analogous point load free body diagram. W times D2 divided by 2 So that was the total value of this load. And it takes place at some distance d, which is d1, which was that distance, plus 2/3 of d2. This we can use to solve these reactions. We cannot use this in our method of section. We would have to draw our section and then do a new analogous point load. It is only ever good for that singular section we are looking at. Okay, let's look at a simple span beam with a uniformly distributed load on it. Our load is W, so every kilonewton, for every meter, there are W kilonewtons on this beam. Its length is an unknown value L. Here's the good news. This beam right here, this one is probably 95% of the beams we ever design. This is what we do all the time. You are going to do this for your project. Guaranteed, you are going to do this in your exam. You're going to solve these simple beams. In next term, you're going to have to be able to do this very, very quickly. So let's go through and do this with placeholders, and we'll make use of our temporary analogous point load free body diagrams. Remember, it is not the same thing as the overall free body diagram. I'm going to stop this for a minute and have a drink of water. Okay, let's write out this problem. So we're going to do a simply supported beam with a uniformly distributed load. All right. We have this beam here with an unknown load applied to it. Our load is W in kilonewtons per meter. This isn't moment. If it's kilonewtons per meter, it's telling us that every meter of this beam has that many kilonewtons of load on it, and it's spread evenly across the entirety of this. We have an unknown reaction R1 and an unknown reaction R2 because we want to know what it takes for this beam not to move up and down, slide back and forth, and spin. So there's also an unknown reaction Rx right here. And the length of this beam is L. We don't know what the length is. So this is our free body diagram. This is the free body diagram. We can use an analogous point load to find the reactions. So find reactions using analogous point load. All right, so it's really the same beam, and instead of this load, we're saying right in the middle we have the equivalent value of load. Well, every kilonewton length, every meter length of this beam, we had W kilonewtons. So now the total kilonewtons of this is the length of this times the load on it. So this is WL kilonewtons. All right, so P is now WL. We have our unknown reactions R1, R2, Rx, and the length of this is still L. So this is just a temporary free body diagram using analogous point loads. This is the free body diagram of the system. This is temporary. So please, 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 in your final project, I ask for you to draw the free body diagram. You'll need to draw this to find your reactions, but you also at some point need to give me this diagram because they are not the same thing. This is only helpful to find the reactions. That's it. This has a very different meaning about what's happening inside this beam. So this is a handy trick to find the reactions. Let's sum the forces in the x direction, with everything going in this direction being positive, well, Rx equals 0. That one's pretty handy. Let's sum the moments about the z-axis, with everything spinning in that direction being positive. And whenever I'm solving for reactions, I usually pick this very first support, or R1. So I'm going to put my thumbtack right here. I have WL trying to spin it in that direction. That is the negative direction. So I have minus WL trying to spin it in that direction. To be a moment, you need a force and an eccentricity. Well, where is this taking place in our analogous point load? It is taking place at 1/2 L. So times 1/2 L. All right, thumbtack still here. R2 is trying to spin it in that direction. Curl my fingers in the direction it's trying to spin it. My thumb is pointing upwards, so it's positive. So plus R2 times L equals 0. All right, bring this over here, and we have positive 1/2 WL squared equals R2L. Let's divide both sides by L, and we get that R2 equals 1/2 WL. Or, if we call WLP, 1/2 of that. So basically, take all of this load, spread over its whole length, find the total load, which is that, and half of it goes to this side. So this is very similar to what we did before. So half of this goes to this side, or half of this goes to this side, which I think we can infer what's going to happen over here. Let's sum our forces in the y direction with everything upwards being positive. Okay? We have R1 going upwards, WL going downwards, so minus WL, and R2 going upwards, which was positive 1/2 WL equals 0. Bring both of these over to the other side, and you have WL minus half of WL, and R1 equals 1/2 WL. Both of these are in kilonewtons. Oh, hold on a second. My kids love, keep giving my kids these balls from the dollar store, and they're scented. And all of a sudden I could smell like a chemical blueberry smell. And that's because this had been on the front porch, and somehow it came in here this morning. I'm in here feeling like I'm in a barf from fake blueberry smell. All right. If I have strawberry shortcake dolls from when I was little, so we're talking like the year they came out, 1982, and those strawberry shortcake dolls still have the smell. So the blueberry one still smells like blueberry. I don't know what chemicals are in that. It's gotta be wrong. Okay. So we found the reactions for this. So these are the reactions. We use this temporary free body diagram to solve for the reactions of this actual free body diagram. All right, so now we know what R1 and R2 are, but we want to know what the internal forces are in this. Now, I said that you make a section every time there's a change. Well, doesn't it look like there's a change all the way across this? There is, but it's a steady state change, right? The same thing is happening everywhere along its length. Let's try making a cut somewhere between 0 and L. Let's just do this as a temporary placeholder. So we're going to do method of section at x equals 0 to L. So somewhere along this length, we're going to make a temporary cut of this. So let's draw our free body diagram of that. So we have our section. We know we have a reaction here, that was R1, which is 1/2 WL kilonewtons. And just to be thorough, that's 0. And we have W, which is in kilonewtons per meter. This is our length X. We don't know how far over we've cut this, so we're using a placeholder X here. And we want to know what it takes for this object not to move up and down, slide back and forth, and spin in space. And we know that there are internal loads here that are connected to the other half of the beam that are holding this portion of it in place. Some internal shear value and some internal moment value. We don't know what they are, but we want to find out what they are. Solving for a uniformly distributed load on something is a bit of a pain. Let's use a temp analogous point load to solve this problem. So let's just redraw this with its own temporary analogous point load of this free body diagram. Okay, so we have our member there. We know our reaction doesn't change. This is still 1/2 WL kilonewtons, and that's still 0. And we are going to turn this W value into an analogous point load. The value of this is what was under this curve, really. Or we're saying for every meter length, we have W kilonewtons. The length we're using is X here. So the value of this is WX kilonewtons. Okay, so that's how long this portion of load was. We know that it is taking place at half of X. Okay, because this is X. If it was a triangular distribution, that would be a different story. And there is something holding this in place. All right, now we can use this to solve for these unknown internal shear and unknown internal moments. Let's sum our forces in the y direction with everything upwards being positive. Okay, we've got 1/2 WL going upwards, so plus 1/2 WL. We have WX going downwards, so minus WX. And we have minus V. We can rearrange this and find what V is. V equals 1/2 WL minus WX. I just brought the V over to the other side. So anywhere along the length of this beam, V equals 1/2 WL minus WX. And this is in kilonewtons. Let's sum our moments about the z-axis. We want to know what it takes to be in static equilibrium. Everything spinning it in that direction is positive. And remember, I'm lazy. Whenever I am solving, spinning the moments about a section, I always pick right where I cut. So I'm going to spin it at point X. So I'm going to put my thumbtack right here. Okay, if my thumbtack's right here, this reaction is causing it to spin in this direction. Curl my fingers in the direction it's trying to spin, and my thumb tells me that's negative, or minus 1/2 WL times, and this is X away from where it's trying to spin. My thumbtack was right here. Okay, put my thumbtack right here, and WX is trying to spin it in this direction. Curl my fingers in the direction WX is trying to spin it, and my thumb tells me it's positive. So plus wx, and it is half of x away, or 1/2 x away. V passes right through it, so it doesn't cause it to spin. And moment, this m is what we want to know what it has to be to hold this in place. And we've drawn it as being positive. Let's rearrange this and bring it all over to the other side. So this is going to be half WLX over on the other side. And this is going to be half minus half WX squared. So M equals 1/2 WLX minus 1/2 WX squared. All right, well, that's actually not so bad. We have two equations. We know now what the moment is anywhere along this free body diagram. Doesn't matter what the load is, doesn't matter what the length is. We now know what the shear is and what the moment is anywhere along its length. We just have to know if somebody gives us W and the length, we can find out at any point along its length what its value is. Let's keep going with these unknown values though. Let's take a look here. Let's do the little summary. So let's do location, shear in kilonewtons. So we'll do location in meters, shear in kilonewtons, and moment in kilonewton meters. Okay, and we want to know what the value is. At distance x, we know that shear is 1/2 WL minus WX, or 1/2 WL minus WX. And moment is 1/2 WLX minus 1/2 WX squared. We did this. We solved for this. Okay. What if we put in some placeholders here? What if we did it at 0? What if we said x is 0? Okay. So let's plug x as 0 into this. 1/2 WL minus 0 is going to give us 1/2 WL. Let's plug 0 as x into this. Well, that would be 0, and that would be 0. Looks like our moment is 0. Let's look at 1/2 L. So let's look at the halfway point. What if we made x 1/2 L? Okay, 1/2 WL minus W times 1/2 L. Well, that's 1/2 WL minus 1/2 WL. Our shear is 0. Interesting. Let's plug 1/2 L as x into this equation. 1/2 WL, 1/2 L. So 1/2 WL, 1/2 L squared, 1/4 WL squared minus 1/2. I always have to go through this. Okay. 1 minus 1/2 W, 1/2 L squared, which is 1/4 L squared, because this whole thing was in brackets, which gives us minus 1/8 W L squared. And this was 1/4 minus 1/8 gives us 1/8 WL squared. Let's try it as L. So we plug L into here, 1/2 WL minus WL gives us minus 1/2 WL. let's plug L into this. 1/2 WL squared minus 1/2 WL squared gives us 0. We could go through and do 1/4 and 3/4 as well. And in fact, I encourage you to go through and solve it. It's a lot easier when you write it out step by steps and multiply out your fractions. But I'm going to go through and draw this here. Let's draw our free body diagram. Let's draw our shear force diagram, and let's draw our bending moment diagram. So this is free body diagram, shear force diagram in kilonewtons, and bending moment diagram in kilonewton meters. Our free body diagram was, and this was W, kilonewtons per meter. And we had solved for these reactions, and the reactions were WL divided by 2 and WL divided by 2. That's 0. Okay, our shear force diagram, if we went through and solved for this at 1/4 and 3/4, at 0 we found it was 1/2 WL. Okay, so we came up to here. At the halfway point, it was 0. And at L, it was minus 1/2 WL. So this is WL divided by 2, and this is minus WL divided by 2. If we went through and solved for it at 1/4 and 3/4, we would find that this is a perfectly straight line. What's the maximum shear force on this? Let's assume W was factored. Our maximum factored shear load, or our max shear load, is WL divided by 2. Up here we had reaction 1 equals reaction 2 equals WL divided by 2. Look at this. Our shear force equals our reactions. Our maximum shear force is at the reactions. Where is the shear force 0? It's at the midpoint. Well, that seems like an interesting, handy little bit of data too. Okay, let's take a look at our bending moment diagram. At the ends, our bending moment diagram was 0, and at the midpoint, we were WL squared divided by 8. Now, if we went through and plugged this in at 1/4 and 3/4, you would see that, and this is, I always find it hard to draw a parabolic curve. It's not a straight line, and it's not a perfectly curved line. It's a parabolic line. We've got a squared in this, okay? But the big takeaway is at the midpoint, our maximum moment is WL squared divided by 8. Okay, I said that this beam, oh, do you know what I didn't do? I didn't draw that this is L. I have said that this beam is 95% of the beams we will ever look at, right? I said it is the most common thing we do. If it's the most common thing we do, we now know that the reactions are the load times the length divided by 2. The shear, the worst case shear, is the load times the length divided by 2. And we know the moment is the load times the length squared divided by 8. We have the answer for the most common problem we're ever going to look at. Like, this is huge, team. This gives us a massive amount of information. We've now found the majority of the beam problems we need to solve, right? If this is the most common thing we do, then this is the most common answer we have, all right? So here it is worked out again for you guys. So using method of sections, we develop the equations that find the reactions and the shear and the bending moment at any point on a simply supported beam. And we found the maximums, right? We found a bunch of data. If this is the most common beam, this seems like really important information right here. I can promise you next term, you're gonna plug this into your calculator like 50 times easily. This is going to be a super common thing we need to talk about. For a uniformly distributed load, we can find now what the worst case shear is and the worst case moment very quickly. In fact, it seems like for most of these beams, somebody's probably done exactly what we've done a bunch of times. Look at this. Uniformly distributed load. We've got length. We've got W. We have some unknown length X. R equals V is WL divided by 2. So the load times the length divided by 2. We did that. But look, what about shear at some unknown point along its length? We did this as well. Moment at center, WL squared divided by 8. They could find moment anywhere along this curve if we wanted to. In fact, this is exactly what we wrote. They just pulled it outside and added some brackets in. Now, this delta max at center, see this big nasty equation? Don't worry about it for this term, but next term, we are going to come back to this. This equation is going to be super handy for us. Remember at the beginning of this term, we found what the maximum allowable load was? The maximum allowable deflection. We found how much we allowed our beams to deflect before we said, ooh, that's a problem. We're going to damage our finishes, and we don't like that. Well, the same way we're going to compare this to the actual reduced shear value or the actual reduced capacity of shear for our beam and the actual reduced capacity for moment on our beam, we will use this to help compare against the allowable deflection. And those three things next year will let us say, this here is a beam that meets all of the life safety requirements, all of the stability requirements, and all of the stiffness requirements we've set out for ourselves. So we can do half of it. We know how to figure out what the allowable loads are. We know how to figure out what the factored shear is and what the factored moment is. And next term, we're going to figure out what we're comparing those to. Okay? Look at this. We also did this one, concentrated load at center. So we've got some real information here. We did all of this. We derived these ourselves. So if we've done it for these ones, it seems like there's probably a lot of other ones that people have already done for us. Look at this one. What if there's a point load somewhere along the length of the beam? They've done this. What if there's 2 point loads equal distances apart on this beam? What if there is a uniformly distributed load on a beam that has a backspan and a cantilever? There's our shear force diagram. There's our bending moment. We can calculate what the maximum values of everything are. Okay, I am going to do one more example for us here where we're going to look at it with these values. We're going to go through and do it by hand just quickly. Actually, no, we just did this. Let's take a look. We can go through and do it at a series of points, but we've already found these equations. Like, we don't have to. We know that we could just plug these locations into the equations we've already found. Some of you might find it handy to go through and manually do that if you would like to. And I wanted to give you worked out problems here because you guys are gonna have to do a method of sections one. It is okay if you do it with placeholders and then plug it in with your known values. Or you can go through and do method of sections with your known values and pick several spots. I'm okay with both ways. But for your projects, you have to do method of sections for the beams I've provided you. All right? They check on me on accreditation that I have made you do that. So we've got to work together on this. You guys have to do method of sections for that. But other than that, you're done with it. You know how to do it. You know that a bunch of people have done them. What happens if we have a beam though, that isn't one of the normal basic ones? What if we have a really unique loading condition? What do we do then? Okay, so I have provided a few more examples that you guys can work through. I know some of you, I've gone through everything you need to know for this lecture, but I know some of you like more examples. So over the years, I've added more worked out problems for you to have to review. For those people that are really, really like to go through step by step again and again and again. So I've provided some more where I've given you the problem, and then you can go through and cross-check your solutions if you would like, okay? And then I've shown you how you can find that same information on one of the example beam diagram loading tables they've already given you. This is one that they had worked out in there. So we have a backspan, we have a cantilever, we have a uniformly distributed load. Here it is worked out by hand with method of section. But look at this one. We have a uniformly distributed load and a point load. That one doesn't seem as normal, does it? That one seems like a partial uniformly distributed load and a point load. Now, some of you have probably heard of superposition. It is a concept that is used across the majority of fields of engineering. They use it in electrical. Almost anywhere you can integrate. You can do it in two separate problems and add them up, or you can go through and make X an unknown along this portion, and then make X an unknown along this portion. Boom, did it for you. So for those of you that would like to, you can go through and solve this yourself, but it's worked out. I wanted to give you as many worked out problems as I possibly could. I can tell you they're not going to be this complicated on the exam. So if you can go through and understand half of these, you will be great on the exam. But I know some of you panic if you don't have the hardest thing you can imagine to do. So I've tried to give you the most complex ones that would be reasonable for you to encounter. And I can tell you I'm not going to give you ones that are that hard in the exam. But it's handy to see the process here. So these are for you to review and look at. Okay. Forever tips. Shear tends to be worse at the ends where we have our support. Moment tends to be worse at the middle. Let's go back and look at those. Okay, we had a high shear here and a high here shear. We had the worst moment here. So somewhere in the middle. It's not exactly at the middle on this one. But you can see that there is some combination of the uniformly distributed load and some combination of this. The shear is going to be worse at either of these ends here. It depends where this is positioned, to be honest. Let's take a look at the other ones. Okay. This one had a cantilever, so it was a little bit different, but our shear was the worst at our supports. So maybe that's a better way to talk about it, is saying that the shear tends to be worse at the supports. And maybe I'll even go update that comment for you guys, because it really seems to be the worst at the supports here. And our moment is worse at the midspan here. It looks like there's something funny happening where our support was as well here. Oh, thank you. Ooh. Beer with lunch, fancy. So you can see that there's something funny happening here. There's a negative moment. That seems like instead of it bending this way, it's bending that way. Well, we could imagine if this was a cantilever, right? And we had something holding it down here, and we put a point load here, it kind of makes sense that it's going to bend in the opposite direction that we're used to. So it does make sense that we'd have a spot with a negative moment. This one, worst shear is at the supports, and the moment is worse somewhere in the middle. Okay, so that seems to match. Oh, now I've managed to leave my slideshow. Damn it. Let me just rather than restart the slideshow, I will just do this. Okay, Studying tips. You need to know how to do method of sections on a beam. And it's even better if you know how to do it without numbers. You should understand that the analogous point load is not the same thing as a free body diagram. It's a handy little trick we can do to make a temporary free body diagram to solve for the reactions. Those reactions might be the end of our method of section. They could be the thing holding our section in place. You should know how to draw the shear and bending moment diagrams. Don't forget your labels and units. Determine the worst shear and moment for those beams. So pick out what the worst values are. And then you should be able to cross-check your supports, your your shear diagram, your bending moment diagram, your worst shear, your worst moment with the beam loading tables. Because next year, we're not going to do method of sections. Most of the beams we're going to do already have those beam loading tables done for us. In fact, most of them are going to be this one right here. So after the end of this term, you're not going to have to do method of sections anymore. You're going to be able to go straight to this and look it up. But we do have to do it for the project. For the exam, do it however you want. Maybe I'll ask you something where you need to do method of sections, but I can't see the work you're doing, so I don't know if you determined it from the beam formula or from method of sections. It's up to you. But for the project, you have to do method of sections. If you only use the beam formula, you're gonna lose a chunk of points. So those are some easy points to get because I've already gone through the process for you. We've gone through it together. So most of the work is done. Like you can copy it really, but I need to see you do that process, okay? So next week is kind of a light week where we're going to talk about kind of when and why and where we would moment connect things. And we're going to talk a little bit about deflection, really. So there's no assignment for this week, but I have uploaded for those of you that like to practice assignment questions with worked out solutions as an assignment solution sheet. Just because I know some of you really feel that panicky need, but I can tell you they're not going to be harder than the two I worked through. Anything I test you on isn't going to be harder than those two I worked through for you in the slideshow. If you guys really want to go further, you feel free to Google method of section beam analysis, and you will probably find a ton of examples out there of people going through that same thing. You can see if you like the way they talk about it better. Maybe that works well for you. I looked up a few on the internet, and I looked at them, the worked out solutions. You're probably gonna like mine better. They made it look very complicated, and they tricked you with arrows drawn in both directions. But if you need to do that, I'm not going to judge you. Sometimes it's helpful to hear something in a different voice. I am totally okay with that. What I want you to do is get the information into your brain. Okay, one lecture left next week. See you then.